everyone. Welcome to the fourth interaction session for control systems. So I'm your TA, Soumya, and I am a PMRF fellow, a PhD student at IIT Gandhinagar. So this time we are going to cover mostly second order systems. We are going to have some sample problems related to second order system, and further when we delve into the problems, we'll see how to design or what kind of controllers are available on a standard basis, and where are they applicable, which controller we are supposed to use when. So we'll be seeing all of them. Okay, so we'll start with the problems now. Okay, so I'll show you the question. So the first question is, a second order system is governed by a differential equation. The differential equation is given here. So we want to know if it is underdamped, overdamped, undamped, or critically damped. So how do we find the answer to this question? So based on just the prior knowledge, whatever we had done till week 3, we know very well that we need to convert this into Laplace domain, because solving differential equation in time domain is not as easy as Laplace domain. You get a chance to solve the algebraic equations there instead of differential equations. So we'll go to the frequency domain. Okay. So how we would proceed? Here it would be Laplace transform of y double dot t is, does anyone remember? Okay, I'll solve this problem. Okay, yeah, s square 2s, very good. So it would be uh, s square ys plus 4sys plus 2ys is equal to us. So we are supposed to find out a transfer function. You know very well that when we are trying to find out a transfer function, we take all the initial conditions to be 0. So when you try to expand y double dot t, it would have the terms of the derivatives also, y dot 0 related to the initial conditions, but we do not need them here because it is transfer function and the initial conditions are 0. So we can write ys upon us is 1 upon s square plus 4s plus 2. Now what are we supposed to find out? We're supposed to find out if the system is underdamped, overdamped, or undamped. So what would help us to find out all of these things? So there is you might have read about zeta and omega n. Zeta is the damping ratio and omega n is the natural frequency. Without any input being given to the system, the frequency which is already there in the system is known as natural frequency. If there is some input, then it is going to change. We are going to deal with such questions later on. As of now, this is the natural frequency of the system. Now, we need to find both of these terms to tell that it is underdamped, overdamped, or undamped. So let's see what was taught in the lectures to you. So when you dealt with the second order system, it was very well clarified in the lectures that the governing equation is of this kind. So you really have second order differential equation here. On solving this equation by converting it into Laplace domain, then applying you converted here into Laplace domain. But then you have to find out the transfer function. Because you need to find out transfer function, you took the initial conditions to be 0. The transfer function that you got for the system was of this kind: omega n square upon s square plus 2 zeta omega ns plus omega n square. So this was a transfer function you found out for the system ys upon us, and then When you found the poles, it was S is equal to minus zeta omega n plus minus omega n under root zeta square minus 1. So we are supposed to compare this PS equation, this whole, uh, we are supposed to compare this equation with what we have found to determine what is zeta, what is omega n. Once we are able to find out what each of them are, then we can classify the systems as under. So if it is under damped system, so what is under damped system? When there could be cases, no, zeta could be greater than 1, zeta could be 0, zeta could be 1, or it could lie somewhere in between 0 and 1. So based on all, and it is always positive. So if it is lying in any of these, it falls in any of these categories, it is going to show some effect. The system is going to show if it is going to dampen the response, the output response, or it is going to over damp it, or it is going to have some overshoot and then it is going to damp. So it could be anything. So based on what is the value of zeta, so in the first case, we see that if zeta is in between 0 and 1, as shown here, it is under damped system. Okay. And what are the poles here? In this case, obviously, if zeta is less than 1, this would mean that there would be a j term here because it is under root of zeta square minus 1 and zeta is already less than 1. That means the term inside the root is going to be a negative quantity. If it is going to be a negative quantity, definitely अगर इसको 1 minus zeta square लिखा तो there would be a j coming out. So that is why this term is there. And then we know that we can always write omega d. So omega d is just the replacement. And we write omega d to be equal to omega n into under root 1 minus zeta square. So this is also very important. In short, if zeta is in between 0 and 1, it would be under damped response. It would have the poles at this location. So this is very important. We'll be solving all the questions today that would have the reasonings related to the poles of the system and everything. So you need to be thorough with this. In case you forget at some point of time, you already know this would be the transfer function omega n square upon s square plus 2 zeta omega n s plus omega n square. You can derive from here also that what could be the poles of the system. Okay. If zeta is equal to 1, it is going to be critically damped. So you see, if you put in this equation, when you have had the poles of the system in the first case, if you put zeta is equal to 1, definitely the second term is going to die out and you're just going to have two poles at minus zeta omega n. Okay. So when you have two poles at minus zeta omega n and zeta is equal to 1, so you have two poles at minus omega n. So this is going to be the scene. Another case is when the system is overdamped. Overdamped means zeta is greater than 1. So you see, we are increasing the damping ratio. So in the first case, it was zeta बहुत ज़्यादा नहीं है, means we are not having much of damping. Zeta is equal to 1 means we have increased the damping. Zeta is greater than 1 मतलब damping बहुत बढ़ाया है. And the poles here are as follows. Okay. Now you see in this. Uh, Okay, so these are the cases that we are supposed to cover. Moreover, please refer to this diagram also. So this diagram is really important. This would also help you everywhere. So see, when you had this term here, minus zeta omega n in the first case, and the second term you had j omega d. Okay, this was your case. So you see, when it is plotted here, in this S plane. Then on the imaginary axis you have g omega d, j omega d. On the real axis you have minus zeta omega n. It is just from here and here. You can see that it has 2 points here. And when you take the, see, so when so if you try to find out, I'll change the color of the pen. If you try to find out what is the magnitude of the a point that is present here or how far it is from origin, then you can just do this under root of z minus zeta omega n square plus omega d square. And when once you do this, you will find that this length is equal to omega n. So this has been given as omega n. So it is on the real axis This j omega d is on the imaginary axis, and you can see that this would eventually give you omega n. Okay, so yeah, so in the first question that we were doing, we were basically supposed to classify what kind of system it is, overdamped, underdamped. So you know the three cases, you know this transfer function. Compare the value of omega n and zeta, and let me know uh, what zeta value you get. So if you try to see, you can compare it to omega n square plus s square plus 2 zeta omega n plus omega n square. Okay, when you compare this, one another thing you can see is that here omega n square, if you compare, you would get 1. Here omega n square, if you compare, you would get 2. That is just a matter of constant. What we can do is we can put 2 here, and we can always multiply it by 1 by 2. Okay, so eventually you have to find out omega n from the denominator term only. Make sure there is no coefficient of s square already present there, because that is what the standard form of the transfer function is for uh, this kind of system, for the differential equation you have, and for what we have derived also for second order system. So s square, there has to be no coefficient, and then you can just compare and find out what are omega n and what is zeta. So when you find, what you get is omega n is equal to root 2, right? And 2 zeta omega n is equal to 4 in this case. So zeta is equal to root 2, right? Yeah, it's root 2. So zeta is equal to root 2. That means this lies in which of the cases? So zeta is equal to root. Ayan, you answered a question. You said 0.707. Why did you say that? I think there is
Ma'am,
some.
I did a mistake, calculation mistake. So
Yeah. You would get root 2 only, 1.414. You might have divided it somewhere by 2. Okay. So what you get here is zeta is equal to root 2. Zeta is equal to root 2. That means that uh, the value of zeta lies in between. Sorry, it is greater than 1. It is greater than 1. Then it means that this case was for overdamped system. Okay. So the answer here is overdamped. So this is the way you are supposed to classify what kind of damping is there in the system. Okay. So this is how we'll proceed. Another thing is, so from intuition also, you should understand what is underdamped, what is critically damped, what is overdamped. So when you try to find out the response of the system, let's say a door is there. Okay, a door is there and it is not highly damped. Matlab, it can be like the door swings to and fro. It goes out, it comes in, it goes out, it comes in, and after certain number of oscillations, the oscillations die down and then it settles to zero. So that is the case for this underdamped system. Whereas there could be another extreme case where the door is like, once you go out, you leave the door open, it would not have any oscillation to and fro. It would slowly come, and it would come to the steady state position. That would be a closing of the door. There would be no overshooting on the other side. So that is the example of overdamped system. So this is with high damping. This is with very low damping, and there is a case called critically damped system, in which you just damp the system, and it is not very high zeta also, but you don't experience any overshoot on the other side also. Okay, so when you have this under damped system, what you see is there is a time where when the response y reaches the steady state value. So in our case, steady state value is 1, as shown here. It reaches the steady state value just for the first time. This is called rise time. So there would be a concept of rise time also. You might have already read them in the lectures, but this is what you do. Then this is maximum peak overshoot. Means how much overshoot you have when you compare it to the steady state value. So one was your steady state value and you have reached somewhere here. So what is the percent? What is the percent you're overshooting? Okay. So this is the maximum peak overshoot. Then there is a thing called peak time. That means at what time you are achieving this peak overshoot. So that is the peak time of the system. And there is a concept of settling time. Settling time means when your response is settling, see it is coming down, it is coming down. When it goes into 2% of the region, 2% of band of the, for example, if it is 1, what is the plus 2% and minus 2% for 1? If it settles in that band, then it is set, that response is settled, and whatever time you get corresponding to this whole settling means जब वो 2% बैंड में फर्स्ट टाइम आया, what is the time it took to go there? So this is known as settling time. So it is defined in two ways, either 2% band or 5% band. So you might have seen the formulas of both of them that are taught to you are different. Okay, but this is the way how we define. So we'll have the questions later on also, but this is for telling the difference between the damped systems and how do you classify, how do you tell that what is the performance of the system, means if it is having high rise time or low rise time. uh, so you want to know how the system is performing. So in that case you need all of these things. Okay, we'll proceed to the second question. A second order system is governed by this equation. What is the natural frequency of the system? So again, you can convert it into Laplace domain. And can someone tell me what you would get ys upon us? If you are able to find this out, you can just compare it with omega n square upon s square plus 2 zeta omega n plus omega n square. And then whatever value of omega n you get is the natural frequency of the system. Yeah, right. The answer is 3. It is because when you try to find this, you get 1 upon s square plus 3s plus 3. And when you say this is omega n square, so sorry, plus 9, and this is omega n square, so omega n is 3. So this is your answer. Okay, we'll move to the third question. In the same question, we want to find a damping ratio also. So that is also easy. 2 zeta omega n has to be compared with 3. And you know 2 into zeta into 3 is equal to 3. 3 cancels out and you get zeta is equal to 0.5. Okay. So when you get this equal to 0.5, you can take this answer. So this was really the basic of understanding of second order system. Now what we want to do is, okay, so you knew that it was the uh, natural frequency that was governing there because there was no input given to the system. Now to the same system, we are going to give some input. Okay. So what was the transfer function? Ys upon us is equal to 1 upon s square plus 3s plus 9. Now, what we say is that we want to give a unit step to the system. Unit step means ys upon 1 by s. 1 plus s. Okay. So, if you see, it is going to be 1 upon s into s square plus 3s plus 9. So this would be the case when you have given the unit step response to the system. So what did the question say? That the frequency of oscillations in the unit step response of the system. So now you cannot say that 9 would be the frequency of my system because you see there is a s already there and it is not fitting into, it is not equal to omega n square plus s square plus 2 zeta omega ns plus omega n square. It is different now. Okay. Um, do you want to say something? Okay. So now what we'll do is, so yeah, these both cannot be compared. When these both cannot be compared, we need to find out some frequency of the system, and it would definitely not be the natural frequency of the system. So how we are going to find out? We are going to use the already the ways that we have used were like what? Ys is equal to, we wrote it as, how did we write this? See, we wrote this as s plus s square plus 3s plus 9. Okay, so it could be written as, if we try to simplify, because we have to, you know very well that we have to go into partial fraction method, and when we go to partial fraction method, it has to be broken into some a by one term plus b by some term plus c by some term in all those ways. So we'll try to see if this is a perfect square. It is not a perfect square already, we'll make it a perfect square so that it goes into some sort of sine and cosine terms from where we can get the frequency of the system. So we'll try to do this. So what we'll do, we will let it be as it is, and then we will write this as s square 2 into s into, we wanted 3 to be here, right? 3 by 2 plus 3 by 2 square. So we have made perfect square out of this. So we need to subtract the term that we have added. So we will subtract minus 3 by 2 because this was the extra term, 3 by 2 square. This was the extra term we had added, and plus 9 was already there. Okay. So now when you try to solve this, you can write it as s into s plus 3 by 2 whole square plus 9 minus 9 by 4. 9 minus 9 by 4 would mean 27 by 4, right? So it would be 27 by 4. So you can proceed with solving of this. So it can be written as a by s plus b into s plus 3 by 2 plus c, because this form is of quadratic type, and hence we need to use bs plus c wala method, and since we have converted into s plus 3 by 2, we'll use this, and here it would be s plus 3 by 2 square plus 27 by 4. We can solve it to the end, but the question asked does not require solving to the end, because it just asks us the frequency of oscillation in the unit step response of the system. It is just asking the frequency. See, there would not be any frequency contribution from this side, because whatever value of A you get, it would be A ut only and nothing else. So no frequency contribution from here. But you see, a frequency would be contributed from here in the form of sine or cosine, because in the denominator, what you have is s square, it is of some sort of s square plus omega square term, which you already have, which you already had in the sine and cosine term. So this is your omega square. So what is your omega? It is under root 27 by 4. So it is 3 root 3 by 2. So 3 root 3 would be, you should get this kind of answer. It should be 1.5 into 1.732. So this is your answer, 2.6 radian per second. Okay. So because an input is provided to the system, you need to find out what is the response or what is the frequency that is present in the system now. And this you would get only when you get sine and cosine term, and this would be available like this as square plus some term. So you've got the answer. Okay. Okay. So yeah, there was a problem two. Problem two had what? You need to find the rise time for the system. Okay, so in problem 2, you had found zeta to be zero point 0.5, omega n to be 3. This is sufficient. You had found zeta to be zero point 0.5, omega n to be 3. Now we want to find out what is rise time of the system. Okay, so you might have gone through the lectures, and when you went through the lectures you might have seen that there are many performance specifications given for under damped system. When a unit step is given to the system exhibits a behavior that I showed there, and for under damped system you have certain performance specifications. So I'll show. So, see, so this was what I was also talking about that time. I'll change the color. Yeah, this is about what we were talking. So, this response, the underdamped system response. So, after making all the calculations that were taught to you in the lectures, you came to know that rise time of the system is time taken to reach 100% of its final value for the first time. For the first time is very important. Okay, this is like not every time we reach, only for the first time. So in this case, this is the first time when we have reached the final value of 1. Okay, this is the first time when we have hit the threshold, the steady state value. So this is going to be rise time for us. This whole time is rise time. Then what happens? Peak overshoot means what overshoot you have. So this part, जो steady state value चाहिए थी, how much we have overshooted. What is the amount by which we are uh, running, what percentage we are running more than the steady state value. So it is basically going to be a fraction only कि 1 से कितना percent overshoot मारा है. So this term would help us to do that. The time at which, so how would you find this peak overshoot? It would definitely be by making the gradient 0 for YTP. Okay, then at what time we have got the overshoot? This is the TP, which is peak time, and settling time is when you go into 2% band. So this whole time is TS. Okay, now whenever you try to find out the rise time, it is going to be this. This is after all the derivations that are given to you in your lecture notes and you have read. So rise time is going to be this. Okay, rise time is going to be this, where beta is cos inverse zeta. As I showed you in the first, okay, I forgot to state this to you when when I was showing this angle is beta. And this beta, when you try to write cos of beta, what it is going to be? It is going to be this upon this. So this is omega n 1 minus zeta square, right? Am I writing it? Sorry. I wrote it wrong. Sorry. Uh, cos beta, when you are going to write down, it is not going to be this or this. This is going to be for sine. It is going to be this upon the hypotenuse. So this is zeta omega n, and this is cos. This is omega n. Omega n cancels out, and beta you get is cos inverse of zeta. Okay, so that is the relation only present here as well. Okay, so here when you write the beta, here is cos inverse zeta, and this is, and omega d is omega n under root 1 minus zeta square only. Okay, so this is our rise time. Peak time is, and again here omega n under root 1 minus zeta square is omega d. Maximum peak overshoot has this formula, and when you see the formula you can very well understand that MP is 1 plus e to the power pi zeta upon 1 minus zeta square. Okay, so this is a term. Now, when you see, you'll find that, so this is the final term, this one. So you'll see that as you increase zeta, zeta jitna बढ़ाया, this whole term will be less. मतलब, as zeta increases, maximum peak overshoot decreases. If we take the same example of the door, if we increase the damping of the system, matlab, damping of the system means it should be damped, the oscillation should not be there, it would not make an overshoot in the other direction. It would not reach the steady state value and go above that and come back and settle. वो पहले से ही डैम्प होता रहेगा and it would eventually reach the steady state value. That is why this relation is there. That if zeta increases, maximum peak overshoot has to be less. If zeta is less, damping ही कम है, then overshoot will be there. Okay. So that is why this is the case. And then this is settling time. Some there are proofs already given. And for 2% band means you want to settle in 2% of the steady state value. Then it is going to be 4 by zeta omega n. If you want to settle in 5% band, definitely the time taken would be less because you want to settle, you don't want to have much reaching to steady state. You're fine with 5% here and there also. So it is going to be 3 upon zeta omega n. So this is the mathematical calculation also that was taught to you in the lecture. Now, we want to find out here what is the rise time for the system. TR is the thing we are interested in. And here when you write, so, okay, what was your rise time? It was pi minus beta upon omega d, right? So first we need to calculate what is beta. Very important. So beta is cos inverse zeta. So cos inverse of 0.5. Cos inverse of 0.5 is pi by 3, right? 60 degrees. Then once you get beta, so this is beta basically. Beta is equal to pi by 3. Okay. Now what we need to find out? Omega d. Omega n 1 minus zeta square. So what is your omega n here? 3. 1 minus 0.5 का square. So 3 into under root मतलब 1 minus 0.25, so it would be 0.75 मतलब 75 by 100. So it would be 3 into uh, you can write it as 25 threes are 25 fours are, so it would be 2 and here it would be root 3. So 3 root 3 by 2 is omega d. Okay. So what is rise time then? Here pi minus beta by omega d is the value. Your pi minus pi by 3 upon 3 root 3 by 2. Okay. So it is 2 pi by 3. It is going to be pi by omega d, right? It is 2 pi by 3 into 2 by 3 root 3, right? And check the value. Can someone tell me if the answer matches to any of the following options? 4 pi upon 9 root 3. 0.8. Yeah, we have 0.8 here. Okay. So the rise time is 0.8 seconds. Okay. So yeah, we have found out the rise time. Similarly, we are going to solve for the other performance specifications also. Okay, so we very well went through all the performance specifications. Now for the same question, where zeta is equal to zero point 0.5 and omega n is equal to 3, we want to find the peak time. Okay, peak time is Tp. What is Tp? Pi upon omega d. That means pi upon omega n 1 minus zeta square. That means pi upon 3 into under root 1 minus zero point 0.5 square. 3 into 4, oh, sorry, 2 pi upon 3 root 3. 2 pi upon 3 root 3 is the answer. 1.2. Okay, thank you. Very good. So 1.2 seconds is the answer for this question. Okay. Similarly, we want to also find the maximum peak overshoot for this question. So zeta is equal to 0.5, omega n is equal to 3. Okay, we want to find the maximum peak overshoot. So how do we find? MP in percent we want to find out. It is e to the power zeta pi upon 1 minus zeta square. You already have the value of zeta and you need to multiply it by 100 to get the percent. Please tell me the answer to this question. So you can see maximum peak overshoot just depends on damping. It has no relation with natural frequency of the system. So this is important. That is why we could give a direct relation between zeta and maximum peak overshoot. That what would happen if the damping is increased, what would happen if damping is decreased. Okay. Let me know the answer to this. Yes. The answer that you'll get here is 16.3%. Okay, so this is the way we solve. Another parameter that the specification that we want to find out is the setting time of the system. So let's say we want to find this down in 2% band only. So if I want to find out in 2% band, TS would be 4 upon zeta omega n. So 4 upon zeta was 0.5 and omega n was 3. So basically 8 upon 3. So when you try to find it out, it would be 2.67 seconds. So we have the answer here. Okay. So this is the way we find the performance specifications. Okay. So the next set of questions that we'll have the questions on controller also. And you might have already gone through the lectures. So what controller is? So you read that when we were talking about the negative feedback system, and then we said that okay, this is the controller, it takes the error, it gives me some output that goes to the plant. Now what is this controller going to be? How is it going to provide an input to the plant that helps me reach the steady state or some desired value of the output that we want? So let's say, so what was the actual control diagram? So it was, this is my reference input. Okay. Then I have this summing block. This is my error. Error comes somewhere from the feedback that I'll draw. The error is passed to the controller system. The controller gives me some control input that is processed by the plant or the system, and then you get the output. You take the output, you multiply it with some gain, and then you pass it here. So here it is negative sign, that means it is negative feedback. Okay. So what, so you know, what is this controller? How do we decide what type of controller should be preferred? Because this is already known. So this is a system, you cannot change the system, right? This is the output that you will anyway get from the system. This is the reference that you want at some point of time, that okay, I want the motor speed to be 1500 rpm. So you decide the RS. This is just the feedback from the output. This error is processed by this controller. Now we want to know what should be this controller, so that it gives me some control input that goes into plant and brings the or gives me the desired output after the feedback. Okay, so this controller is the thing that we are going to see now. So there are many types of controller. So one of so again I said this is the error, this is the control input, and this is the controller. So this is our controller transfer function is US is equal to CS upon ES, CS into ES. But see, US is here, ES is here, CS is here. So US, sorry, US would be CS into ES, right? That is why this is written here. Now, uh, okay. So this is a bang bang controller. Bang bang controller means it is just if else kind of thing. If the error is, say, let's say my tolerance is 0.5 units. So if the error is less than 0.5, turn this controller, otherwise take this control input. This is a very simple on off controller. The next controller that is important that we'll see is proportional controller. So what this controller is, ये जो control का place है, replace it by some constant kp, just a constant, no s, nothing. It is just going to be proportional to the error that you have. So you get an error, you multiply it with some constant to get us. So this is what is being done here. So here proportional controller is ut is equal to kp into et. Okay, so kp here is proportional controller, and this is the sorry, proportional gain. Okay, so US here is kp into es, where cs is equal to just kp. It is going to be gain and nothing else. So it is a very simple controller, and it leads to non-zero steady state tracking error, because for steady state tracking, for reducing the steady state error to zero, we already have a integral controller. Okay, so we'll see here. The second thing is integral controller. In this, what we do is, instead of, so here also we have again ki. Okay, but that ki is not multiplied with the error, rather it is multiplied with the integral of error. That means summation of error, whatever has happened from 0 up until now. So ut here is some constant into error integrated over the time. Okay, so this is the type of controller. Now you have read very well in the Laplace transform that if there is an integral term, you get s in the denominator. If there is a differential term, you get s in the numerator itself. So here us is equal to ki upon s into es. So cs here basically is ki upon s. When you write this, you can see very easily that you have a open loop pole at s is equal to 0. You have a pole at s is equal to 0. To always remember that when you try to introduce integral controller in the system, you are going to introduce a 0 pole at s is equal to 0. Okay, so it was taught that it can lead to zero steady state error, right? Yeah, it introduces an open loop pole at 0, and actuator saturation is also possible here. Now in derivative controller, what we do is, so in the last time when we wrote integral controller, we were integrating the error throughout. This time we are differentiating the error. So ut is kd into differentiation of the error. So now I hope you're able to make this difference. So when we had just proportional controller, just proportional, what we did, ut is equal to kp into et. In when it was integral, we integrated this with d tau. When it is differentiation, what we are doing is we are taking the same thing and we are differentiating it with time. Okay, so this is the thing we are doing, differentiation. So yeah, we are differentiating it here, and then us can be written as kd into s into es. So here your controller is kds. It introduces uh, 0 at 0. Okay, similarly, if you try to combine proportional and integral, that means you are going to have kp into the error term plus ki into the integral of the error term. So it is going to be kp for this and ki upon s for this. So this is your controller, proportional integral controller. Okay, when we want to have proportional derivative controller, kp into et, kp into error plus kd into differentiation of the error. So this is your controller. Proportional integral derivative, you'll see everywhere later on that we'll be using PID controller. So it is एक बार proportional के लिए किया, एक बार integral के लिए किया, एक बार derivative के लिए किया, and we are going to write it here like this, and it introduces both of these things. So this was important. Okay, so these are the types of controller that you have already seen. Now, which of the following statements is true about a proportional controller? So for proportional controller, what we have seen, the uh, this is wrong. There is no complex variable there. It would lead to zero steady state error. No, it does not lead to zero steady state error. This is done by integral controller. Okay. Then the control input is inversely proportional to the error. No, it was ut is equal to kp into et. The control input at an instant of time is dependent only on the value of the error at that instant of time, right? So if it is at this time, at e is equal to t, you get the control input at that instant of time only. Means it does not integrate, it does not differentiate, it just takes into account that instant only. That is why. So your answer is this. Okay, moving on to the next question. Okay, since we have already solved the question, okay, you know about stability. Can someone tell me, let's say a transfer function is given to you. How would you find out if the system is stable or unstable or marginally stable? 。  . 。  . 。 . 。 . 。 . 。 . 。 . 。 . . 。 . . . . . 。 . . . 。 . . 。 。 . 。 。 . . 。 。 。 . 。 。 . 。 。 . 。 . 。 . . 。 . 。 Can someone tell? Right. Poles, if the poles are in the left half of the S-plane, then it is going to be stable. So this second order system is given to you and it is governed by the following equation. We want to find out if the system is stable or unstable, what kind of thing it is. Okay. So what you're going to do is you're going to take the Laplace transform for this. So what will get? S square ys. Again, we are trying to find out the transfer function. So initial conditions would be 0. S square ys plus sys plus ys is equal to us. So ys upon us would be 1 upon s square plus s plus 1. Okay. Uh, then you can find out the poles of the system. So what would be the poles of the system? Minus 1 plus minus under root b square minus 4ac by 2. It would be minus 1 by 2 plus minus j root 3 by 2. Right? So this is the pole of this. This is the these are the poles of the system. So when you draw the S plane, this is your imaginary axis. This is your real axis. Since the real term is negative, minus 1 by 2. This is minus 1 by 2 plus this is j axis. So this is one pole. This is another pole. Minus 1 by 2 plus j under root 3 by 2 is here. Minus 1 by 2 minus j under root 3 by 2 is here. So both the poles lie in the left half of the S plane. Hence the system is stable. So yes, this is your answer. Okay. Now what we'll do is, okay, so this is already given to you. Okay. That yeah, the system is stable and you had the transfer function as this one. I'll copy this transfer function. Okay, this is the transfer function of the system, of the previous system, because we're going to do something related to problem 10 only. Now, let's say a unity negative feedback closed loop control system is designed with the above system planned in problem 10 using a proportional controller, with KB being the proportional gain. The closed loop system is stable for what? Okay, this was the differential equation. That means this is the transfer function of the plant. Now I want to have a controller. So what has happened? This was your RS. Okay. This was your plus minus. This was your ES. This was your CS. This was your US. This was your PS. This was your YS. And since it is unity negative feedback, so we'll take HS to be 1 only. Okay. Now, uh, so first thing is the closed loop system is stable for. We want to do everything for the closed loop system. See, if you want to do everything for the closed loop system, then you are supposed to have closed loop transfer function in the first place. Okay. So closed loop transfer function for this system is ys upon rs, right? This would give you the closed loop transfer function. This is gs upon 1 plus gshs. So this is what we have read for the, yeah, this is what we have learned, that for negative feedback closed loop control system, this is the transfer function. So what is gs here? Gs is cs into ps. Whatever you get in the forward path is gs. Okay. HS is 1 year, right? So if so, in our case, we have a proportional controller. That means CS is equal to KP, right? So we can write GS to be CS into PS, and this was our PS. This thing, this thing was our PS. This whole thing is our GS. Okay, so KP is our CS into PS is 1 upon S square plus S plus 1 upon 1 plus Kp into 1 plus S square plus S plus 1. When you try to solve this, what you'll get is Kp upon 1 plus, sorry, S square plus S plus 1 plus Kp. So this is the closed loop transfer function that you've got. Okay. Once you've got this as the closed loop transfer function, then we want to say that how we can ensure the stability of the system. The closed loop system is stable for what? So when you want to ensure the stability of the system, you have to make sure that the poles lie in the left half of the S plane. It should not lie elsewhere. So let's see what are the poles of the system. Because if we anyhow find what are the poles of the system, and then we check that if they lie in the left half of the S plane, we are going to ensure that the system is going to be stable throughout. So what is the characteristic equation here? S square plus S plus Kp plus 1 is equal to 0 is the characteristic equation. What are the poles of the system? -1. We'll have many other ways of finding out the same thing, but the point is it would be done later, I mean in the next week of the course, when you learn about Rauther's stability criteria. So that would give you a much easier way of determining if the system is stable or unstable. Since we have not been into that, we will simply check if the poles are in the left half of the S plane or not, and hence derive the condition for Kp if it is uh, going to make this system stable or not, or for what value it is going to make the system stable. Okay, so if we try to find out, what we'll get is -1 plus minus 1 minus 4 into 1 plus Kp, right? Or I'll write Kp plus 1 now, for now. Kp plus 1 upon 2. So it would be minus zero point 0.5, or let it not be minus zero point 0.5. Okay, okay. Minus zero point 0.5 minus 3 minus 4 Kp by 2. Okay, so these are the poles of the system. Now we want to make sure that both of these poles, both of these poles should lie in left half of the S plane. Now how do we make sure if both are lying or not lying? So what we'll do is, first we will take first P1 condition. P1 is minus zero point 0.5. Let's say I'll take -1 only first. Okay, minus 3 minus 4 Kp by 2. So now see, this term is already negative. So what else do we want? We want this whole term. Hello, am I audible? Am I audible now? Okay.
Yes.
Okay. Yes. Okay. So see, this part is already negative, right? This whole part should also be negative, right? पहला वाला पार्ट नेगेटिव है, सेकंड पार्ट को भी नेगेटिव होना पड़ेगा ताकि we get everything in the left half of the S plane. So if this is negative, this is making the term negative, then what we must ensure is, okay, what, Just a second. Just a second. Okay. Yeah. If we take P2 to be minus 0.5 plus minus 3 minus 4 Kp. Okay. If we take this value, if we take this pole, then what we have to see is, since it everything should lie in the left half, so this minus 0.5 is already there. Now the second term should also such that it should be less than 0.5. Minded point less than 0.5, क्योंकि minus 0.5 is already there. Now anything that is being added to it should not be higher than 0.5, ताकि so that it makes the entire term positive. We don't want to have entire term positive. Okay, we just want to have this term do not cancel out minus 0.5 effect. मतलब this whole term by 2 also, this whole term should be less than 0.5. If you try to put in this condition, it would be uh, minus 3 minus 4 kp is less than 1. Okay, minus 3 minus 4 kp is less than 1. So minus 4 kp is less than 4 kp is less than minus kp is less than 1, kp is greater than minus 1. This is the condition that you get from here. So this is one of the options over there. Similarly, you can proceed in this way also. So this term is already negative term. What we want is just that this term should be negative. We just want this term to also be negative only. So if this term needs to be negative, so minus, no, we need not use this condition. This condition sufficiently gives you. So we need this term to be less than 0.5, and hence you get Kp is greater than minus 1. That's enough. And next time we'll see Raut-Hurwitz criteria, which will also help us to make sure that we check the value of Kp so that the system is stable. Okay. Now, okay. The closed loop system in problem is expected to track a unit step reference input. Okay. I think I have to teach you something before that. So you already know that ys upon rs is equal to gs upon 1 plus gshs, right? You already know this. Now let us and you note the you also know the final value theorem. What does final value theorem say? So when you want to find out the steady state error, you have to find limit s tends to 0 s into ys. So this is your for when you want to find out what is the not steady state. When you want to find out what is steady state value for a response. So this is the way you find out. Now what is happening here is you already know that a Planck transfer function is this. Now es upon rs can be written in this way. Do you agree? So how we'll check this is ys upon rs, you know, it is equal to gs upon 1 plus gs into hs. Okay. Now you can write ys. Okay. So you can write ys upon rs to be equal to this. And after this, you can write okay. So before doing that, what we'll see is es upon rs can be written in this format. Okay. So es can be written as rs upon 1 plus gshs. So steady state error, which is ESS, is limit e tends to t tends to infinity. So limit SES. Okay. So what you have to put limit on is S into RS upon 1 plus GS into HS. Uh, I wanted to explain this, but somehow just wait for 2 minutes. Okay, okay. Yes, yes. What can ys be written as? Ys can be written as s upon gs upon rs is equal to gs upon 1 plus gshs. How I have written this? See, when I showed you, when I showed you this, what can, how can this be done? Ys can be written as, this whole is gs, right? Gs. So ys can be written as gs into es. So ys, uh, so like that only. So when you write ys upon rs, here I have replaced this ys only by gs into es. So that is why this has come. So I have written es into gs as this quantity. Now see, gs cancels out, and what you get is es upon rs is equal to 1 upon 1 plus gs hs. This is what you saw here. Okay. Once you see this, you can write es to be rs upon 1 plus gshs. Once you have rs upon 1 plus gshs, Then you can write steady state error to be ESS limit t tends to infinity because it is steady state. Similar thing can be written like this in the Laplace domain. S tends to 0 and E into ES. Okay. Once you write this, you can write replace ES by this RS upon 1 plus GSHS quantity. Hence, you get this to be the steady state value. Now, when we are trying to solve this question, we'll use the same technique. And what we'll do is, we will you try to find out steady state error. It would be limit S tends to 0, S into RS upon 1 plus GS into HS. Okay. Limit S tends to 0. Now, what you find? uh, Step reference input. That means RS is going to be a step input here. Your reference is going to be a step input. S into 1 by S upon 1 plus, and what you had GS into HS here. This was your this. This was your GS into HS, right? KP upon S square plus S plus 1. S cancels out, so it becomes 1 upon limit S tends to 0, 1 upon 1 plus Kp upon S square plus S plus 1. Put S is equal to 0, you'll get 1 upon 1 plus Kp. Okay, so this is your answer to this question. So this derivation will come again in the next week probably, and you'll see this. So this is used to find out the steady state error, and that is only the thing which we have used. Before this, what we were doing is we were doing this for output. So output का अगर steady state value जानना होता था तो we used to do limit s tends to 0 s into is. Here it is steady state error value, so error के लिए we'll do this thing. Now we don't want to find out just the steady state output. We want to find out what is the steady state error present there. Okay, that is why. This is an important concept. Okay, which one of the following is true about an integral controller? So we already saw that it does introduces open loop 0. This is wrong because it introduces open loop pole, because ki upon s is the transfer function. So it introduces open loop pole. It would always lead to non-zero steady state error. No, this is also wrong because it leads to non-zero. It leads to zero steady state error. So it should have been zero steady state error. The control input at any instant of time depends only on current value of the error. No, it depends on the integral of the error. Right? Eat out, eat out. It depends on this. So this is also wrong. It can lead to actuator saturation. Yes, we had read this. This is correct. Now, which of the following is true about the derivative controller? Does derivative controller introduce open loop pole at 0? See, it was Kd into S. Cs was Kd into S. This introduces open loop 0 and no pole, because S is not in the denominator, no. So it would introduce a 0. So this statement is wrong because it says pole. It would provide a non-zero control input in presence of non-zero constant error signal. No, it would not provide, because it takes the derivative of the error. So if the error currently is non-zero control input is there, then also it is, if there is non-zero constant error signal, then it would provide a zero control input, because it takes a derivative, and it would, if et is constant. Okay, so det by dt would be 0. So it would be zero control input, and it says non-zero control input. Then this statement is also wrong. The control input at an instant of time depends only on past values of the error. Past values of the error only integral dependent, because it took 0 to t. This does not depend on the past values of the error. Takes the differentiation. So this is also wrong. It is anticipatory in nature. We have seen this. This is the correct option. Okay. So, okay. These were the questions that we had to discuss, and we are done with the today's lecture. In case you want to ask anything, you can ask.
Thank you.
Yeah.
Ma'am, I have a doubt in question 3.
Question 3. 1 minute. Yes. What is the doubt?
No, I think it is question 4, where you calculated frequency of oscillation per event.
This one?
Yes, ma'am. Uh,
Okay.
can we can we calculate directly from the transfer function by
So,
comparing?
so is this transfer function and this transfer function same? Is this same? You have an S
Ma'am,
term
but
here, no?
if we do ys by 1 by s, then the transfer function will be same because
Yes.
ys equals.
Yeah, yeah, continue. Hello?
Yes.
Yeah, so you want to say that if we just had this ys upon us, then it was happening, right? You got omega n is equal to 3.
Yes, and the transfer function does not depend on the type of input of the system.
Yes,
So
transfer
can
function does not depend. So see the questions that have been asked. See, I'll show you. So in this question, how this question is different from that question. Here, a second order system is given to you, and you are being asked the natural frequency of the system. Natural frequency is the frequency obtained when there is no input given to the system. Okay. So here you have got the answer as 3. Whereas in this question, see what you are being asked. You are not being asked natural frequency of the system. You are being said the frequency of oscillation in the unit step response of the system. जब यूनिट स्टेप रिस्पॉन्स दिया गया जब यूनिट स्टेप इनपुट दिया गया then we want to know what is the frequency of oscillation. Means it is the system is now not behaving naturally. It has got some forced response. It is not exhibiting just the free response. तो उसको forced response आया है तो it is going to have an input as well. So transfer function पहले था. Now it is no more transfer function when you have US already there and you have multiplied it over here. अभी multiply कर दिया है इधर US को लाके, because you have got some input and that input is going to tell what is the response. So the questions are only different. There it was related to transfer function. In this case, it is related to response of the system. It is not for transfer function of the system. So oscillation, now you have to tell the frequency. What is the frequency you are obtaining when unit step is given as an input to the system? In that case, it was that no input is being given. It is just the system. It is the transfer function of the system. Tell me what is the natural frequency of the system. So both these questions are different.
ma'am, then can we calculate omega d for this question?
Omega
Because
d.
because it is the angular frequency at which system tends to oscillate.
So it is damped natural frequency only. It is a way of representation only. Omega n into 1 minus zeta square, under root 1 minus zeta square. You won't be able to calculate. You can calculate that for, so it is damped natural frequency. You see, natural frequency is again there. So if it is a transfer function representing a system, you get what is the natural frequency of the system. Then you can find out, okay, omega d, I'll find out. It is omega n into 1 under root 1 minus zeta square, and it is a damped natural frequency. In this case, since there is already an input, you won't be able to. You'll have to find out if this input is given, what is the frequency of the response of the system. So you cannot
Okay,
compare.
ma'am.
Okay. So in the next, I think we are going to have this steady state error thing only, and more on controllers in the next week. So we'll have problems on them, and maybe we'll start with MATLAB sessions soon because you are way into the course. Good way you have made into the course. So probably we'll start with MATLAB sessions. But yeah, for this, for today, this was the thing. So thank you. We'll meet next time on Monday at the same time. We are meeting on Monday. Thank you.
Okay, thank you.